The world's oceans are big, really big. Like if you stacked all the water on top of each other, they would reach the height of over 148 million Empire State Buildings. But despite their immense size, our planet's oceans have one peculiar feature. They don't mix. If you've ever taken a road trip along a coast, you may have seen two bodies of water that appear to be completely separate, even though they're both salt water. The boundary between them is very clear. You can easily tell where one begins and the other starts. Just look at this image captured by NASA in 2020. You can clearly see the separation between the dark blue water of the Atlantic Ocean and the lighter blue hues of the Arctic Ocean. But there's more. Even if you dive deep down into the ocean depths, you'll still find distinct layers of water that don't mix. So why don't the two oceans mix together? Let's take a closer look. This image showing two different colored waters side by side was shared by the National Oceanic and Atmospheric Administration, NOAA, on Twitter in 2019. The agency did not explain why the two waters aren't mixing, but the reason isn't hard to understand. The darker blue water near the surface has a higher density than the lighter colored water below it. Because of this difference in density, the two waters stay in separate layers. Essentially, the two masses of water are so different from each other that they refuse to blend. But that raises another question. How do you get two different layers of seawater? Well, there are several factors that affect the density of seawater, such as temperature and salinity. The warmer the water and the saltier it is, the denser it becomes. That means that warm, salty water tends to sink while cold, fresh water stays closer to the surface. Let's go back to the NOAA tweet for an example. The dark blue water appears to be colder than the light blue water below it. Since cold water is more dense, it makes sense that the cold water is closer to the surface and the warmer water is deeper down. The reason why the water is cold could be because of where it came from. This image of the two separate bodies of water was likely taken somewhere in the northern hemisphere. That means the water on top could have come from snowmelt or a glacier. Snow and ice reflect a lot of sunlight and absorb very little heat energy from the sun. So when they melt, they create cold, fresh water. On the other hand, the water below it likely came from deeper in the ocean, where temperatures are much warmer. The same thing happens in the Arctic Ocean. There, the surface layer of water is actually warmer than the water below it. It just looks cold because it's covered in a sheet of ice. The ice reflects most of the sunlight hitting it, keeping the surface layer cold. Below that, the water has absorbed heat from the sun and from geothermal vents on the seafloor. As a result, the bottom layer is warmer and less dense. Because of this, the warmer bottom layer of water slowly moves toward the poles while the colder top layer moves away from them. And once again, the two bodies of water don't mix. But what about that picture of the two separate bodies of water in the Arctic Ocean that we looked at earlier? Does it show the same thing happening? Not exactly. It's actually an example of another phenomenon that keeps the world's oceans from mixing. The formation of deep water. Cold water that's high in oxygen is called oxygen-rich water. This type of water forms when cold air causes the surface water to lose heat energy, which also allows more oxygen to dissolve into the water. When the water gets too cold and dense, it sinks down through warmer, saltier water until it reaches a depth where the temperature and salinity are similar. For example, the surface water in the Arctic Ocean is very cold and therefore sinks down to the bottom of the ocean where it mixes with the warmer, saltier water. Over time, the oxygen-rich water gradually heats up, which causes the dissolved oxygen to escape and become part of the atmosphere. Meanwhile, the warmer water that was below it rises up to replace it. This cycle is known as deep water formation, and it plays a big role in ocean circulation. It's also why the water in deep ocean trenches doesn't mix with the water above it. Take the Mariana Trench, for example. It's the deepest part of the ocean and reaches a maximum depth of about 11,000 meters. Down there, the pressure is nearly 1,000 times greater than at the surface. The intense pressure causes the water to become less dense, which prevents it from mixing with the water above it. Water from the surface can't sink down into the trench because it's less dense, and water from the trench can't rise up because it's more dense. And finally, let's take a look at this image shared by the Woods Hole Oceanographic Institution on Instagram in September 2020. What do you think's happening here? You might think that the different colors of water mean the ocean's layers are separating, but that's not the case. Instead, it shows something called internal waves. These waves form when there's a change in water density, and they travel along the boundary between the two different layers of water. As the wave travels, the water sways up and down, creating these beautiful ripples. So you might be wondering why the water has two different densities. Well, that's likely because of a change in temperature. Warm water is less dense than cold water, so the surface water heats up while the deeper water stays cold. As the wave travels, the warm water sways up and down, mixing with the cold water below it. Eventually, the warm water cools off and sinks back down. However, if the water layers are deep enough and the difference in temperature is big enough, the waves can keep going for quite a long time. What's happening in these videos is known as upwelling. Upwelling happens when wind blows along a coastline, causing the surface water to move away from the shore. As the surface water moves away, deeper water rises up to take its place. The upwelling brings cold, nutrient-rich water from the depths to the surface. This can cause a lot of biological activity as the nutrients support the growth of phytoplankton and other marine life. It's for this reason that many of the world's most productive fisheries are found in areas where upwelling occurs. But it can also cause problems. For example, upwelling can bring toxic algae blooms to the surface. These blooms can kill fish and other marine life, which can then wash ashore and create a mess. In addition, upwelling can bring deep water that's high in carbon dioxide to the surface. This can lead to a decrease in the pH of the surface water, which can make it more difficult for marine organisms to survive. For example, some corals and shellfish need a certain amount of carbonate ions in the water to build their shells and skeletons. But when the pH of the water decreases, fewer carbonate ions are available. This can lead to weaker shells and skeletons, which makes them more vulnerable to being broken. There are a few things that can cause upwelling. One is wind. When wind blows along a coastline, it can push the surface water away from the shore, allowing deeper water to rise up. Another is the Earth's rotation. As the Earth rotates, it causes a force called the Coriolis effect. This effect can cause water to move to the right in the northern hemisphere and to the left in the southern hemisphere. This movement can cause upwelling along the coastlines. So there you have it. Now you know why the world's oceans don't mix. From density differences to upwelling, there are a lot of factors that can keep the world's oceans separate. But maybe that's not such a bad thing. After all, it's thanks to these factors that we have the diverse range of marine ecosystems that we do. If you enjoyed this video, please leave us a like and subscribe to our channel for more fun science videos. Thanks for watching.